So let's start our last talk of the conference. I am sorry, Omar, but you are the last one.
Oh, that's fine.
Somebody has to be the last one.
Yeah, and somebody who's.
No. So I'm very happy here to introduce Omar Antolin. It's very smart. So he works at
That will
UNAM.
not be an evidence.
UNAM Seoul in Mexico City is a professor there. So he'll tell us about this bank, crystalline interacting topological spaces with cohomology. Nice.
Thank you, Bernardo, and thanks a lot for inviting me. And it's been a great conference. I think.
I guess now's the time to thank him.
Yeah.
Yeah.
Yeah,
I wasn't sure if you were gonna do it.
I know. And yeah, no, thanks, Bernardo, and
Thanks for coming.
all the other organizers. But yeah, it's been great, and so I'm gonna speak about something that's sort of an unusual topic for me to speak about. I have been working on this for a few years, but I don't normally give talks on this, mainly because my co-author, Daniel Sheinbaum, understands all of this much better than I do. This is a talk in physics. There will be, there's this old adage that you're supposed to give at least one proof. The talk that apparently is not for physics talks, but habits are hard to break, so I will have one proof of the talk. But it is going to be mostly about physics, and I mean, I wish I could say that all I know about physics is what Daniel has taught me, but all I know about physics is a fraction of what Daniel has taught me. He's managed to teach me, and it's proving to be a challenge even for him. But so I won't assume that you know anything about topological phases. I won't assume that I know anything about it either. I'll start going over the basics, and I'll start with a crash course in quantum mechanics. Okay, so quantum mechanics studies dynamical systems whose evolution is governed by the Schrödinger equation. The equation involves a linear operator. So here I'm this psi of x. Oh, I can point at it. Psi of x comma t is what's called the wave function. And the way the wave function for a particle determines where the particle is probabilistic. The wave function is a complex valued function such that if you take the square of its norm, that's a probability density or a probability measure that tells you where the particle is. And the Schrödinger equation is this partial differential equation with a linear operator. And the thing that it is linear on is psi itself, not the norm of psi. So it's not that the probability density evolved has an evolution dictated by a linear operator. What is linear is the value of psi itself, not the square. These features all contribute towards quantum mechanics being somewhat non-intuitive. So psi is not a probability. What's a probability is psi, the norm of psi squared, right? So in particular, you can take a linear combination where things cancel, and then the probability of the outcome is zero. That is the source of some strange behavior in quantum mechanics. Okay, and so what do these Hamiltonians look like? The Hamiltonian is the thing that describes the quantum system that you're talking about, and they can be of many forms. One typical form is this. It has a term for kinetic energy, which is just the Laplacian in the spatial variables, not the. So this is Laplacian only with respect to the variables in x, not with respect to t. And then a term for the potential energy, which is so this here v is x comma t is just a function, and whenever I write a function and operator, I mean the operator multiplying by that. So this is a typical form for Hamiltonians. And all right, so often the Hamiltonian, so I said it could depend on x and t. Often it doesn't depend on t, and if it doesn't depend on t, then there's a simple solution to this differential equation that you could write down. It's just this is the answer that you would expect. I put it in quotes because For example, if H were a bounded operator on that Hilbert space, then you could define this exponential via the usual power series, and the power series would converge, and this would give you an operator that makes sense to apply to this function. But the Hamiltonians that are typically studied in quantum mechanics are usually not bounded. But that's okay. There still exists a solution to that equation, and it's not given by this formula, but it is given by a one-parameter group of operators. And okay, so but for intuition, this formula is good, and it would literally apply if you happen to have a bounded Hamiltonian, which doesn't actually happen. So notice that if this wave function at time 0 is an eigenvector of H with eigenvalue lambda, then by this formula, the way it evolves over time is that it's always just a multiple of its initial value, and it's a multiple with this coefficient. Hamiltonians are self-adjoint operators, so these eigenvalues lambda are always real numbers, which means that this here is a complex number of modulus 1, right? So in particular, the probability densities that the wave function at time 0 and at time t give you are the same. So this is what's called a stationary state. The probability distribution of where the particle is located in space stays constant throughout time, in this case. And all right, so the way you interpret the eigenvalue lambda is that it's the energy, so it's the level of energy associated with the state. And for a large class of Hamiltonians that are typically used to describe systems, there is a smallest eigenvalue, and the eigenvectors corresponding to that eigenvalue are called ground states of the system. And often, in fact, if there's only one ground state, and if there's only one, it's called non-degenerate. And the degeneracy of the system is the multiplicity of this lowest eigenvalue. Okay, and so what topological phases are about is about just roughly classifying systems by which could conceivably turn into others without undergoing phase transfer, right? So if you imagine that you have now a Hamiltonian that is time dependent, right? It's like a system that evolves over time. But for certain kinds of evolution, you wouldn't expect anything too drastic to occur, and that is what's called adiabatic evolution. And what we want to do is classify Hamiltonians by saying to our equivalent if one can evolve to the other over time without undergoing any phase transitions. Roughly speaking, what happens is if the changes to the Hamiltonian are sufficiently gradual, then the behavior of this system is very similar to the case in which the Hamiltonian is independent of time. When it was independent of time, we saw that if the starting state was an eigenvector for the Hamiltonian, then at the end it was still an eigenvector. In fact, it's the same eigenvector just multiplied by. And so there are theorems in analysis that tell you that this happens with an appropriate hypothesis that says that the Hamiltonian changes slope. Okay, so the adiabatic theorem, or adiabatic theorems, there's several related ones. What they say is that if you have a Hamiltonian that satisfies this gap condition, which means that around the lowest eigenvalue, so for any moment in time you have a Hamiltonian h of t, and if all of those have a little interval around the lowest eigenvalue that doesn't have any other point of the spectrum of the Hamiltonian, and a few other technical conditions, but that's sort of the main condition. If those are satisfied, then the system evolves approximately in the same way as a time-independent one would. The state at the end of the evolution is approximately an eigen. If you start in a ground state for the Hamiltonian time 0, after evolving for some time, you'll have something that is approximately the ground state for the Hamiltonian at the end. Okay, so this is the theorem. Right? If the change is sufficiently gradual, then the things behave approximately the same way as the time time-independent ones that have these stationary solutions. Okay, and so we'll say that two quantum systems are in the same phase if there's a homotopy of Hamiltonians between them. If there is one parameter family of Hamiltonians, all of them with this gap around the lowest eigenvalue that varies continuously and connects the two the Hamiltonians for the two systems. That's when we'll say they're in the same phase. So phases are just the connected components of the space of gap Hamiltonians. And we'll often restrict to specific classes of Hamiltonians for systems that preserve this or that type of symmetry. And right, so there is this space of Hamiltonians. What we want to compute is pi model. Those are the topological phases. And you could think instead of pi naught of the space of Hamiltonians, you could think of pi naught of the state of the space of ground states for those Hamiltonians. There's this space of gap Hamiltonians, there's a space of their ground states, and there's this function that associates to each Hamiltonian its ground state. And it's very reasonable to assume that that function is a homotopy equivalence. You can think about it, the fibers of that map would be the space of Hamiltonians that all have a common ground state, right? So these are operators that have that as an eigenvector and have a gap around. If you take a convex combination of two such operators, it will still have that as an eigenvector with different eigenvalue and with a possibly smaller gap. But so this is closed under this fiber is closed under convex combinations, so it's contractible. So this map should be homotopy equivalence. There are a few technical difficulties in this thing. Formally defining these spaces of gap Hamiltonians, you don't just want them to be gap, you want them to be physically realistic in other ways and so on. So making this a precise statement is maybe a little bit difficult, but it's a very reasonable assumption to say that you could classify the topological phases either as connected components of the space of Hamiltonians or connected components of the space of possible grounds. Okay. All right, so now let's start talking about crystals. So imagine a crystal, but that completely fills space, an infinite crystal, the crystal stretching in all directions. What makes it easier to deal with an infinite crystal is that then it really is periodic, right? That's the special property of a crystal. If you look at it closely, you see that it's just this repeating pattern. Of course, it's not actually periodic unless it extends infinitely. This is maybe somewhat idealized, but it's a good model to study first. So we'll talk about infinite crystals. Those have a group of translation symmetries whose rank is the dimension of the space the crystal lives in. And to say that a system preserves the symmetries of the crystal is just that that it's translation invariant by the translations that fix the crystal. That just means that the Hamiltonian itself commutes with the translation operators corresponding to translations by points in this lattice translation. Okay, so lambda here is it's a copy of z to the d, where d is the dimension of the crystal, and the translation operators work on that Hilbert space of L2 functions just by translating the argument.
Sorry, so how do you think about the crystal? Are you thinking about a lattice or thinking about
It's a lattice in R to the
the points or
just the
points
function.
of hyperplanes?
Yeah,
or-
so this lambda, it's a subgroup of R to the D, isomorphic to Z to the D.
Okay.
And lambda, it's no, it's a lattice. So the lambda is just the translation symmetries of itself. It may have additional symmetry. So lambda is
It's
just
growing out wasted.
yes, they'll come in later.
Okay.
Not yet. I would say I haven't introduced them yet, rather than.
So lambda is just a free abelian group of rank.
Lambda is a free abelian group of rank D for a crystal in RZ, and lambda serves double duty. It is the set of sites in the crystal, but it is also the group of translation preserving. And okay, so a Hamiltonian preserves the a symmetry if it commutes with the operator that just applies the symmetry to the argument, these L2 functions. Right? So remember that this F came from the Hilbert space L2 R3 cross R with values in C. The R3 is where X lives. And we're thinking of these at each slice for a particular time as functions defined on R3. And the way you apply a symmetry to the function is just to apply it inside. Right? And if the Hamiltonian commutes with that symmetry, it means that the system will evolve to if it starts in the state that exhibits that symmetry, it will preserve the symmetry as it evolves. And okay, so and here right now this is written here just for translation symmetries, but I'll leave the same kind of commutation relation for other symmetries later on. Okay, so I showed you some typical Hamiltonians for systems. A time independent one of the typical examples I showed you would have again this kinetic energy term and then this potential energy, and now the potential only depends on X, not on T. And so this part definitely computes with any translation. Multiplication by the function v of X will only preserve translations if V is periodic. Right? So for a periodic potential, this system preserves translation symmetry. Okay, so it's to analyze systems like this that have this translational symmetry. Bloch's theorem is very helpful. The way it's commonly stated in physics says that that for a Hamiltonian that has this translational symmetry, you can find a basis of wave functions that are eigenvectors for the Hamiltonian, and that are of the form, this form, e to the I k dot x times u of x, where u is periodic with periods in the lattice lambda. And so this function here, e to the I kx dot x, is just a convenient way to parameterize the characters of the abelian group lambda, right? Think of when x is in lambda and k is in the reciprocal lattice, then this is exactly a homomorphism from lambda to S1. Right? The reciprocal lattice is the set of vectors in R to the D whose inner product with all of the vectors in lambda is integral. Okay. So this is just a convenient way to write the characters. I'll switch to a more invariant notation later.
U depends on B.
Sorry?
U depends on B in some way, or
right.
Yes, H is-
This is actually for anything
okay.
that has translation. So here's a sort of a more functional analysis point of view of Bloch's theorem. There's a part that's completely independent of the Hamiltonian that I'll explain first, and then I'll say how the Hamiltonian comes in. So first of all, this K from the previous slide, it's really a sort of coordinate-full way of denoting a character on lambda. Just think of a character homomorphism to S1. And then for each character K, you can look at functions for which translating by points in the lattice multiplies by the value of the character. Okay, so look at functions such that for all R in the lattice, f of x plus R is the character applied to R times f of x. That is a subspace that I'll call H sub k of the Hilbert space on which the Hamiltonian. Okay, and so the big Hilbert space is sort of a continuous version of a direct sum of all of these Hilbert spaces, H sub k. You get what is technically called a direct integral decomposition over this space of characters.
So S1 is U1.
Yes. It is. And right, so in a direct integral decomposition, what this means is that the Hilbert space over here is the space of L2 sections of these spaces. So these form a bundle of Hilbert spaces over the space of characters. And the direct integral is notation for the space of L2 sections of that function. Okay. And all right, so this only had to do with the Hilbert space. I decomposed the Hilbert space into a sort of continuous direct sum of all the subspaces where translation acts by a given character. Now, if H commutes with all translation operators, it restricts to each of these subspaces. That's a very easy check. You can just check that if H commutes with the translation operator, with all translation operators, it restricts, it applies to vectors in HK, you get a vector in HK. So that means that it also decomposes as a direct integral of operators defined on each of these small figures. They use small in quotes because they're all okay, so that's the block theorem describes sort of more in terms of bundles of Hilbert space. And so it turns this single Hamiltonian into a continuous family of Hamiltonians parametrized by this torus, which is the group of characters. Okay. So from Bloch's theorem, so here I'm going to explain how symmetry is what brings topology into the picture. So far, we didn't have any interesting space whose topology would be relevant to us, but having this translation symmetry through Bloch's theorem gives us a torus. And so we'll get something defined, some kind of invariant for the torus as a result of our classification. So we have the torus. It has, that just came from decomposing the Hilbert space. It didn't have anything to do with the Hamiltonian. But if the Hamiltonian is translation invariant, then you additionally get a function from, right? So you get, you have this bundle of Hilbert spaces, so you can consider the associated bundle of operators on those fibers. But that's actually making it sound more complicated than it really is. Kuiper's theorem says that the unitary group of the Hilbert spaces is contractible. This means that all bundles of Hilbert spaces are trivial. So you can identify all of those HK spaces with a single Hilbert space. And so this means that the function that takes a character K and associates to it the Bloch Hamiltonian H of K, just a continuous map from this torus of characters to a space of operators that serve as Hamiltonian. And there's some further theorems from functional analysis you can use. If if your original Hamiltonian was gapped, then almost all of the HK will be gapped, all except the set of measure 0, and you can take it back to a continuous representative where they're all gapped. And so we've turned the entire system, encoding just the translational symmetry, into a function, continuous function from the torus to space of gapped linear operators on a single Hilbert space. And now for each of these, we could take the ground state for each of these Bloch Hamiltonians, and the ground state is just some subspace of this now fixed Hilbert space. So we actually get, just from the translation invariance out of the Hamiltonian, we get continuous map from the torus into the Grassmannian of M planes in Hilbert space. And the most common case is M, or the most important case is M equal to 1. That's when the ground state is non-degenerate. Okay. So you can see the yes. All right. So now, traditionally, in the study of quantum systems, this torus of characters, which is called the Riemann zone, is really only used for single particle systems. And I've really only been talking about single particle systems for now. But so what do you do? How do you represent a particle system with many particles? So take the Hilbert space you're using for the Hamiltonian of a single particle system. If you wanted a system with n particles, you could take the n-fold tensor power of that single Hilbert space and put some Hamiltonian on it. You would start with the Hamiltonian for a single particle, And that gives you a Hamiltonian on the tensor power of the following form. You take products of the form, you take the identity in every factor except in one factor where you put the Hamiltonian for the single particle system. You do this in n possible ways and add them together. And that would be the Hamiltonian for n particles with no interactions between them. And then to that Hamiltonian, you could add another term that specifies the interactions between the particles. Okay, so that's how you write down Hamiltonians from multiple particle systems. You sort of start with, say, my n particles are this. I start with the Hamiltonian for the particles separately with no interaction, and then add some interaction terms. And that you can do this on the tensor product. You can do it on the symmetric power for bosons or on the alternating power if you're dealing with fermions. And these direct sums are Hilbert spaces. The bar there indicates the completion. Take the direct sum as Hilbert spaces. And
Because you don't need it.
sorry?
For the fermions, you
Right. But it would look like that. Yeah. So okay. So so people often just don't use Bloch's, or I don't think people had Bloch's theorem for this many particle case. But mathematically, there's no reason not to use it, right? The point of view I explained on Bloch's theorem that has been known for a long time, the functional analysis point of view, that just needs a separable Hilbert space, and they're all isomorphic to each other. So these Fock spaces for bosonic particles or fermionic particles, they came with the structure, but they're just Hilbert spaces. You can apply Bloch's theorem equally well to them. What you lose then is the physical interpretation of some of the things that go with Bloch's theorem. Those characters K, they represented momentum of particle before, and now they're kind of a sum of the momenta of all particles. That's just not. You really, because it doesn't give you the individual momentum of each particle, it's just sort of a sum of all of them. I think that's what probably turned people off from just using Bloch's theorem the same as before. But you could use Bloch's theorem same as before and just say, for a many particle system, possibly with interactions, this Hilbert space is now one of these guys, right? Or rather, you apply the Bloch decomposition to these Hilbert spaces, then identify all of the fibers with a single Hilbert space. That's this H, right? But so exactly the same, you get a continuous map from the Brillouin zone to the Grassmannian. And so these homotopy classes of maps from the torus to the Grassmannian and planes in Hilbert space, they're also invariants for these crystalline many particle systems, even if they have interaction. Okay. So Bloch's theorem to decompose a Hilbert space, that doesn't even mention the Hamiltonian. If you also want the decomposition of the Hamiltonian, that needs to be translation invariant. And I just wanted to point out something about the translation action that we're using. So this is what a typical Hamiltonian for a system with n particles might look like. These are the Hamiltonians for each individual particle, and this is a term that indicates the interaction between the different particles. And there are many other forms that are considered. This is a simple example. And so notice that here, translating a single one of the xi's is not a symmetry of the system. It's a symmetry of this part, but it changes this part. If you just translate all of them simultaneously, that is a symmetry of the entire system. And so the way lambda acts is by translating all of the spatial variables at the same time, not just one. That's sort of something that
why you don't necessarily need individual.
yes, it's exactly the reason we don't get it. So so maybe it makes things a little less physical, but exactly the same math works. Okay. All right. So we want to consider systems that crystals that don't just have the translation symmetry, that have some additional symmetry. The symmetries of crystals are well studied, but it's a complicated problem. I just wanted to point out how many of these groups there are. If you look at crystallographic groups in different dimensions, I think probably everybody knows that there's 17 planes crystallographic groups. In 3 dimensions, it's 230. And, the number just grows incredibly quickly. And I'm pretty sure we don't know the number for dimension 7 and 9. I don't know how many of these groups there are. But, whatever, if you're, fortunately here, we're mostly interested in. But, all right, just indicate, there's a lot of crystallographic groups. One thing that's fun to do with parties is to, look at tiling and identify its symmetry group. There's this nice algorithm devised by Brian Sanderson. It's a decision tree. If you're like staring at one of these pictures and you want to say what crystallographic group it is, you start by looking at the highest order of rotation symmetry that you see. Then that leads you down one branch, and then it asks questions like, is there a glide reflection? So, and leads you to the correct one of the 17 crystallographic. This particular picture depicting Brian Sanderson's decision tree for crystallographic groups like offer Borel. Okay, so all right. So we won't be able to deal with all possible crystallographic groups. If you have a crystallographic group, it has this subgroup of translations. The quotient by the group of translations is called the point group, and some crystallographic groups are the semi-direct product of their translations and their point group, and some are not. And sometimes there is no section to this production. The ones that do have a section are called symorphic. I don't know what that means. Symorphic means it's a semi-direct product. That's the definition. And so if you have a Hamiltonian for a system that could be in any number of particles with interaction, and it preserves symmetry given by a crystallographic group G, which recall just means that the Hamiltonian commutes with the operators that apply the symmetry to the arguments, so do all of the spatial arguments simultaneously. Then besides what we already had in the block decomposition, you can check that you get a residual action of the point group on this Riemann zone, which was the force of characters with the lattice. You get an action of P on the Hilbert space that you identify all of the fibers of block decomposition to. And you get an action, an induced action of P on the Grassmannian then. And the map that sends every point in the torus to the ground state of its block Hamiltonian is equivariant for these P actions. And this is just checking the work. Okay, so there are other kinds of symmetry in these systems that I am not talking about. I just want to mention these are important. It's not, I'm not covering them not because they're not important, just because they didn't fit into our work. But if you get into this literature, these are important symmetries that you should be able to. Yes. So we discussed spatial symmetries. Those you have some isometry, and you have this operator of precomposing with the isometry. The Hamiltonian is required to commute with that, right? But other symmetries are, for example, this particle hole symmetry, this time reversal symmetry. Those are expressed as anti-commutation and commutation with some operator. There are some choices. The operator can be chosen to square root plus the identity or minus the identity. All of these, all 4 combinations here have different names in the classification of possible types of symmetry. And but what makes these special is that these operators, chi and theta, aren't linear maps. They're anti-unitary. So if you write down what what either one of these 2 equations means for the HKs, recall that the HKs were just the restriction of the Hamiltonian for this subspace of functions where translation acted by the character K. Right? Since these are anti-unitary, you pick up a sign in the phase. So instead of landing in the subspace for the same character, you land in the subspace for the inverse character. Right? That's very different from these spatial symmetries. For the spatial symmetries, what happens with the block Hamiltonians is they just commute with the same operator S. Right? the big Hamiltonian commutes with S, that just implies that all of the little Hamiltonians HK. But it's different for these anti-unit. Okay, so, you know, these symmetries have like a different kind of formula. And we're not going to deal with them. I just wanted to mention these are important, and there's more types of symmetry that you might want to handle in classification topological.
Does this theorem you have in all Hilbert bundles and trivialized? Apply for equivariant Hilbert bundles?
No, I don't think so. Okay, so what Daniel and I did is I've explained it already, but let me just state it again. If you're looking at gapped quantum systems, possibly with interaction that respect the symmetry group G, the equivalence classes of P equivariant adiabatic evolution of these systems is given by the space of the set of P equivariant homotopy classes of maps from the torus of characters on lambda to Grassmannian n planes in Hilbert space, where n is the degeneracy of the ground state. And you know, this Hilbert space carries an induced action of P. So this space, this Grassmannian also has a P action.
I have a question about, you're assuming that the whole topological information lying on the bottom states, but sometimes they're on the top states that are still up below the gap. You may not have anything interesting in the first, I don't know, 10, but in the next
Yeah.
20, you have from invariant.
Yeah.
But you're taking it out because you decide to take only the.
Only the ground state, yes. Yeah, the classifications tend to make this assumption that like only the low energy limit matters. So we'll see this again later when I talk about it in invertible phases of this stuff with PQFTs.
But it needs real crystals. This will not be a good classification. You can give a crystal material for which this will not classify the topological question. You need to put all bands below the Fermi level. All. You need to add all bands below the Fermi level and the theorem will be. But if you
Right.
just put just the bottom one, just because you want it to be connected, and it's not going to put the other pieces. You need to put the whole spectrum of
And we
energy.
fudge the Hamiltonian, push all those things.
Yeah, that was fine.
No, because it's a real thing. Energy is what the energy is, not what we want it to be. You cannot just push down the energy level in real crystal. The energy is the energy. Come on, the energy is. That doesn't matter.
We can talk about this. Okay, so let me just explain that we can simplify this answer, at least in the non-degenerate case, when n is 1.
Can I clarify, is it the bosonic statement or is it?
Oh, yes, yeah, sorry, for the fermi, you can also handle the fermionic case in this setup, but you do get it looks basically the same, but you don't have the point group, you have a central extension of it by it's there in the fermionics. Okay. Yeah, this is the bosonic version. But the fermionic one is unlike adding time reversal, that does change. Okay, so we have right. So if you're only interested in translation symmetry, you have homotopy classes of maps to the Grassmannian, which are already pointed out is CP infinity. It's a AZ2. So there's no, if the symmetry group you're interested in preserving is only the translations, you just get H2 of the torus. Now, if you want to also preserve a larger group of symmetries, right? The crystal has a larger group of symmetries, and you're interested in phases that preserve all of that symmetry. Then, well, you have this P action on the projectivization of the Hilbert space, and that makes it a classifying space for P equivariant. And there's a theorem of Lashoff, May, and Siegel that says that for compact abelian groups, the universal P equivariant, the classifying space for P equivariant principal A bundles, where A is a compact abelian group, is just given by maps from EP to BA. But this requires the group to be abelian. So this is why we're only doing this for non-degenerate ground states, because then this the symmetry group here is U1, which is U. So in that abelian case, this Grassmannian will be P equivariantly homotopy equivalent to this mapping space, and then by junction you can pass the EP over, and then this now, sorry, this is the typo. This should have disappeared from this side. I should just say BU1. Apologize. And now this BU1 has a trivial P action. So this just means maps from the quotient into, again, BU1, sorry for the typo. And that's just, Borel, the equivariant homology of the force. And so if you look at the P action on this torus, it's not, so you can, you might initially think that if you're taking, so this torus is the classifying space of the lattice lambda. So you might think that if you're taking the Borel construction of that with respect to the P action, you're just getting the semi-direct product you started with. So you just get cohomology of VG for the starting with G. But the action of P on this on the space of characters is actually sort of the opposite action. It's really the reciprocal lattice. So there is, for every one of these crystallographic symmorphic crystallographic groups, it has an evil twin where the semi-direct product is not with the same action of P, but it's with the corresponding action on the reciprocal lattice. And so that's this G star. We call it the reciprocal. Okay. And so let me talk about what you'd see in classifications of topological phases. Normally, I mean, probably, so I'm just mentioning sort of a few highlights from a vast literature, which I know almost nothing about. So I'm just picking a few sort of important steps along the way that proposed some classification of some kind of states. Kitaev in 2009 discussed classifying non-interactive fermionic systems using K theory, and you get all sorts of different kinds of K theory depending on the symmetries that you want to preserve. So he did discuss like time reversal symmetry, the particle hole symmetry. There's a big the paper is called a periodic table. Well, sorry, it has periodic table in the name, referring to like all these possible types of symmetry. Yes, topological. And so then then there was a little bit later came a lot of work on what are called symmetry-protected topological phases, which I'll tell you a little bit more about. Chen, Gu, and Wen, and then later work of Chen, Gu, Liu, and Wen discussed the symmetry-protected topological phases and proposed a classification that for a symmetry group G basically says that they're classified by cohomology of VG in dimension +2. Kapustin tried, so there were some known bosonic examples that didn't fit into this group cohomology classification, and Kapustin proposed an extension which winds up classifying the phases by the oriented ordism groups VG, just the Pontryagin dual of the torsion classes in the oriented ordism group.
My vague memory is these classifications are really small.
Yes,
right?
yes,
Okay.
yeah, and the what motivated Kapustin to start searching for a different type of classification was the fact that there were some bosonic examples, or I believe that didn't seem to be accounted for by group cohomology. Then Dan Fried and Mike Hopkins, in a paper that I think has just been recently published, but it's been on the archive since 2016. They classify these symmetry-protected topological phases by classifying invertible EQFTs. And their classification says that phases are given by the torsion elements in pi n, the Madsen-Wilson spectrum for a symmetry group H that depends on the symmetry type of phases that you're trying to classify. This H is, it's the symplectic group, or it's ON, or it's SON, and the different symmetry classes. They have the entire periodic table that tell you what group to use for each case. And so I also wanted here to mention work by Otto and Johnson-Frade, where they explain that it's reasonable to assume that the phases themselves, the spaces of phases themselves, assemble to form a spectrum. And so you get a sort of tautological sounding classification where the topological phases are given by this generalized cohomology theory that is built out of topological phases. To actually use it, you have to figure out what dimension that's fine. Okay, so let me see. Yeah. Okay, so for this symmetry protected phases, the rough idea is that you consider Hamiltonians sort of like you take little systems like C squared, which could represent a qubit, they're like a small system, and you take the tensor product of one copy of this at each site in the lattice, and then you work with Hamiltonians on that. But it's hard to make this rigorous because naive attempts to write down an inner product here will not make this into a Hilbert space. So one thing that people typically do is to consider systems on just larger and larger finite portions of the lattice, and then take a limit as these systems cover more and more of the lattice. And so you can start by thinking of linear operators that are just linear combinations of operators that are finitely supported in the sense that there are tensor products of operators at each site, but only finitely many of them are copy identical. And so one way you can write down some kind of Hamiltonian is to pick for each finite subset of Z to the D an interaction term for those sites. Like what is the interaction for particles exactly at these locations? And then whenever you pick a finite set of sites, you can get a Hamiltonian by just adding all the interaction terms that are subsets of that set of states. And so for that, you can solve the equation and see the evolution of an observable is given by this formula. And then if you chose the interaction terms carefully, this does converge as you take bigger and bigger sets that cover more and more of the lattice. But this is not easy. It takes a bunch of fairly delicate work and analysis, use star algebras, stuff like that. It's not. There are people making this rigorous, but just want to say it's not that easy. And so the idea of these symmetry protected phases, what does symmetry protected mean? It means that they're phases that two phases can be different equivariantly, even if they're not different non-equivariant. Right? That the symmetry is protecting. In particular, you can pick a particularly simple system, call it the trivial system. That would be something like in this lattice model system, whose Hamiltonian is just the sum of terms at each site. There's no interaction. You have big gaps in each of them, and that would be what you would take as the trivial system. And then these symmetry protected topological phases, you can think of them as systems that, if you ignore the symmetries, you can connect them via a path to a trivial system, but you can't do that equivariant. So that's what it means. That's how the symmetry is protecting them from being trivial. Okay, and so the systems that are meant to be classified by these symmetry protected topological phases are systems with short range entanglement. And what that means is that there's some kind of bound on the interaction. The interaction terms for far away particles, and they have to decay. They have to be small compared to the size of the finite portion of the system you're taking. In the limit, there isn't that. All of the interaction comes from nearby. But again, this is not that easy to make. Okay, and so, and you know, what some of these classifications of symmetry protected topological phases really maybe should be called classifications of invertible topological phases. They're related, but not exactly the same. The different, so I'll explain what I mean. And here I'll be very vague. The idea is that, you know, the phase of a system, the deformation class of it, is supposed to be determined just by how it behaves at low energy. And as you approach these low energy levels, the behavior is more and more accurately described by a topological. It's described by a field theory that's not topological. It has a term that as you go lower and lower in the energy, it just tends to disappear, and only the topological term. And so you're supposed to get in the limit TQFT, and you know the classes of those TQFTs are supposed to classify states. And you in particular get invertible TFTs, just invertible in the sense that they have tensor inverse, all of their values are one-dimensional. And that's what the classification of Fried and Hopkins does, for example. And so let me just show you a quick table comparing the kinds of phases that we were interested in defining with the group cohomology classification of SPP phases for crystalline systems, for example, done by Borel and Nels. And you know, sometimes we get more classes, sometimes they get more classes. And now I just want to quickly argue that this is fine. It's okay. These are different assumptions. It's natural that we get different answers. So, you know, these classifications of SPT systems, or SPT phases, are for systems with the short range entanglement or with the invertible property, which are related. And we were just saying, like, take all of that. So we're definitely we're not assuming the short range entanglement. And the ones that deal with TQFTs, the invertible phases, they also assume that there's this stacking operation. If you have two systems, you can stack them by taking the tensor product of their Hilbert spaces. And then if the Hamiltonians are H1 and H2, you take on that the Hamiltonian H1 tensor of the identity plus the identity tensor H2. That's stacking them together. And they stabilize under stacking with trivial phases. So those classifications either have the property that or force the property that stacking with the trivial phase is the same phase. And you know, maybe all of this low energy limit things really changes things as well. And so, you know, and this makes it just sort of very hard to compare, right? So consider the short range entanglement. We are starting with more systems because we don't assume short range entanglement, but also the relation is different because you could imagine that two short range entangled systems might not be connected by a path of short range entangled systems, but might still be connected by a path that goes through some long range entanglement. So the map from our classification to the other classification is neither injective nor surjective.
There's definitely results.
Oh, okay, yeah. Oh, I'll have to ask you about that. And you know, also because of this stability under stacking with the trivial phase, classification of invertible phases, they don't include phases that are called fragile in the literature. Phases that become trivial after stacking with the trivial phase. But you know, that are not trivial if you don't stack them. And you know, if yeah, I have this is something that Daniel, who understands this better than much better than I do, insists on saying, you know, there could be like a genuine difference classifying these invertible these things. It could be that we use something.
It's longer than also specific in their setup.
No.
Oh, you're referring
Yeah.
to that. Like,
Yes, and I only presented the comparison with Untitled and else because I think I picked the dimension and groups where all of the other classifications were mostly. Okay, and you know, finally, there are some limitations to this classification, which I think is shared by several of the others. just tells you what the set of all the phases are if you have a particular system. It is not easy to, you have to basically solve it to try to figure out which class it corresponds to. Right, and so that is all I wanted to tell you. Thank you.